Hello and welcome. Today we are looking at energy level diagrams, and we are going to look at some simple energy level diagrams and show how the relative energies of reactants and products are shown by these diagrams. By relative energies I mean the energies compared to each other of reactants and products. So the first reaction we're looking at is hydrogen reacting with oxygen to produce water. Here's our formula equation. You might spot straight away that it's not balanced, and in order to balance this we can just add a 2 over here and a 2 over here. That means we now have the same number of atoms on each side, and this is now balanced. And we can also represent this by looking at the particles. So here are the particles that are reacting. We've got a molecule of hydrogen here times 2, so 2 molecules of hydrogen, 1 molecule of oxygen reacting to make 2 molecules of water. And we can see this is balanced because we can count up the different atoms there as well. Now, for this reaction to happen, we actually have to supply some energy. And we supply that energy in order to break the existing bonds. So we supply some energy to break those bonds, and once the energy is supplied, those bonds are now broken and they are ready to recombine to make our water molecules. On the other side of things, we've got energy supplied to break the bonds, but here we have energy released when making bonds. So we have energy released when making bonds over this side, so that energy is released to the environment, and here we've got energy supplied to break bonds, and that's taken in from the environment. Now we can actually do a comparison of these. We can look at the energy supplied and the energy released, and we can decide whether the reaction is giving out energy or taking in energy overall, and that will tell us whether the reaction is either exothermic or endothermic. And there's a couple of ways we can do that. We can actually calculate the amount of energy supplied and the amount of energy released and work it out that way, or we can look at an energy level diagram, and here's one that I've just got ready for you, and we can represent the energy level of the reactants and the products. So over here we put our reactants, so the reactants in this case is hydrogen and oxygen, and over this side we put our products, or product in this case, which is water. And now you can see that the energy of the product is at a lower level than the energy of the reactants. So that means energy has to have been lost in this reaction. And where's the energy lost to? It's lost to the environment. It's given out, and therefore this is an exothermic reaction because energy has been given out. High energy level goes down to a lower energy level. Where's the extra energy gone? It's given to the environment, so therefore exothermic. Now there is another bit of this graph that you often see, and that's the bit that looks like this, and this part of the graph represents a little bit of energy that's actually gone into the reaction to get it started off, and that energy that goes in to start the reaction off is called the activation energy. So this part of the graph here, the little bump, represents the activation energy. That's the energy that's gone in to start the reaction off. Now we can sometimes actually lower this activation energy by using something called a catalyst. Now you know a catalyst as something that speeds up a chemical reaction and is reusable, but in terms of our energy level diagram, we can see how this catalyst works. What it does is it provides a different pathway that has a lower activation energy. So in other words, this is the amount of activation energy that's required. Currently, if we add a catalyst to this reaction, what happens is we get a lower amount of energy that's required, to start the reaction off, and therefore the reaction can go faster. Therefore it speeds up the chemical reaction, and you should be able to draw this extra pathway here when a catalyst is given or added to a reaction. And if you just think that it lowers the activation energy, you can just draw a line that is lower down. Mark schemes often will give you a little bit of leeway in terms of whether it's slightly higher or slightly lower, but certainly has to be lower than the first line up here, and that will tell you how the catalyst works. Now the next thing really is just to make sure we're clear in our minds about what this graph is. What you need to be able to do is to be able to talk about or recognize the relative energies of reactants and products. You should be able to talk about activation energy, and you should be able to comment on and identify energy change of the reaction or of a reaction. Okay, so if we have a graph, our energy level diagram that looks like this could be for any reaction. This is actually for an exothermic reaction, but there are parts of this that you should be able to label. So the first line here represents our reactants. These are the chemicals that are reacting, and the last line over at this end represents the products. And you can see for this one we know it's exothermic because the energy level of the product is lower, so we must have lost some energy to the environment. But also you should be able to identify these regions here that I've drawn the graph as A, B, C. One of them represents the activation energy, another one represents the energy change, and the last one represents the energy release. And I've actually done them in the right order there, so don't need to worry about trying to work it out. But A is the activation energy, as we saw on the last slide. B here is the energy change, so that's the difference between the energy used to break the bonds and the energy produced in making new bonds. And the total energy release from this reaction is part C. So if you want to know the total energy release for this reaction, you could look at part C on the graph there, or it's represented by part C on the diagram. You may have seen part B written down or identified to you as delta H. That's not really required for this exam. If you put this down in the exam, you would get the mark, but your teacher may have spoken about that, and that's how it fits in to this diagram. So here I've got our two energy level diagrams. One represents an exothermic reaction, one represents an endothermic reaction, and by now hopefully you know that this one is the exothermic and this one is the endothermic. Now for the higher tier, you need to be able to explain the difference between an endothermic reaction and an exothermic reaction in terms of the making and breaking of bonds. So for this reaction here, the exothermic reaction, its energy released from forming new bonds is greater than energy needed to break the bonds. So when we're breaking the bonds from our reactants over here, that energy is a certain amount, but the energy released from forming the new bonds is bigger. So that means that the reaction is exothermic. For an endothermic reaction, it's the other way around. The energy needed to break the bonds is greater than the energy released from forming new bonds. So here on this diagram you can see that the energy of the products is at a higher level than the energy of the reactants. So that means energy must have come somewhere in order to make that come from somewhere to make those products, and that has come from the environment. So this is an endothermic reaction. Energy has been provided in order to produce the product, or energy has been taken from the environment in order to produce that product. And it's probably a good idea that you get this under your belt, that you look at this diagram and recognize it as exothermic and this one as endothermic, because you might be presented with a diagram that looks either like this one or like this one in the exam, and if you do know it, that's going to be a good head start for you in terms of being able to answer questions that actually might come up on it. Now the last thing I want to look at is calculating energy transferred, and again this is for the higher tier, and what you should be able to do is to calculate energy transferred in a reaction if you are given bond energies. So here is the reaction that we've been working with for this video, and a better way to show that, it would be like this. That's showing the bonds that are present between the different atoms, and the exam will more than likely give it to you this way. I think it would be a bit unfair if they gave it to you like that and made you do that extra step. The questions I've seen have all given it like this. So here's our bonds that are present in the reaction here, but we can't calculate the energy of the reactants and the products, or the energy required to make and break bonds, because we haven't got the data. So the data will be provided for you, and here it is. We've got the bond and the bond energy. Now it's important to realize that a common unit for the bond energy is kilojoules per mole, so these are all in kilojoules per mole. And how do we work out the energy required to break bonds and make bonds? Well, we just use this table and it works out like this. So we've got 2 H's times 2 over here and bonds and the bonds in between. So here we can use this part of the table. H bonded with H has a value of 436 kilojoules per mole. So we have 436, but there's two of these over here, so we need two of those. So it's 436 plus 436, plus we have also our oxygen, and the oxygen bond energy is 498. And so therefore this total comes to 1370 kilojoules per mole. That's the energy required to break those bonds. What about the energy released from making bonds on the other side? Well, we have H2O times 2, and the HO bond is given here, and there's two of those. I know it's the other way around, OH, but it is the bond between the O and the H. So the way we do that is we have on this side 464 taken from here. We have two of those bonds, so plus 464. That's the bond energies for one molecule, and to find out for two, just multiply it or just add it on again. So 464 plus 464, and the total answer for that is 1856 kilojoules per mole. So we can see that the energy required to break the bonds is 1370, and the energy released from making new bonds is 1856. And what you can do is actually work out whether energy is released or taken in. So if we say we have 1370 to break, take away the 1856, that leaves us with an answer of minus 486 kilojoules per mole. Now we have a minus number, and when you do a calculation like this and you end up with a minus number, that actually tells you that heat is given out and it's actually an exothermic reaction. Okay, so a negative number there shows that it's exothermic. Now we can show this on our graph, and that would look a little bit like this. This is an exothermic. The energy level of our product is lower down than our reactants, and so energy has been given off. This value here is our 1856 that we calculated over here. That's how much energy has been given out, and you can see that more energy is given out than that was used to break the bonds, and therefore the reaction is exothermic. So it might be worth having a go at one of these for yourself. This is a different reaction, not one that we've been working with, and there are a couple of questions here. It says calculate the energy change. Is the reaction exothermic or endothermic? You have to explain whether it's or why it's endothermic or exothermic, and then sketch the energy level diagram for this reaction. So it might be worth you having a go at this now, and once you've done it I can show you the answer. So pause here if you like, if not just keep watching and I'll go through the answer. So to calculate the energy change, we look at the nitrogen and the oxygen. The bond energy for the nitrogen is 945, and for the oxygen is 498, and that gives us an answer of 1443. And in terms of the energy released from producing new bonds, that's 2NO. So for NO it's 630, but we have two molecules of NO, so it's 630 plus 630, and that gives us an answer of 1260. Is it endothermic or exothermic? If we subtract these two, we get an answer of 3. We get an answer of 183, and that's a positive value. So then we know that that reaction is endothermic. Remember we said that if this was a negative number it would be exothermic. So here we go. Is it endothermic or exothermic? There's our answer. It's endothermic. And explain why this is an endothermic reaction. Well, that's just going back to what we said on the previous slide. The energy needed to break the bonds is greater than the energy released from forming new bonds, and that's the reason why. And if we were to sketch the energy level diagram, it would look like this. So that's a run through of energy level diagrams. can be quite tricky, so it might be worth going over one or two more times. Certainly worth recognizing these diagrams, being able to explain what an endothermic and exothermic reaction is. But other than that, best of luck with it. Thank you for watching, and I'll see you again soon.